Next, we are going to talk about the applications of a heap. So heap has many applications. One of them is sorting. Now to sort n numbers, suppose that your friend has already written the heap data structure. You can ask your friend to borrow the heap data structure and use it directly. Then if you have n numbers to sort, then what we can do? We can first insert all these n numbers one by one into the heap. So we just blindly insert them one by one without calling find min, without calling extract min. We just insert them. Insert the first number, insert the second number, and so on and so forth. So after this, we will have all the n numbers stored in the heap. And then we can perform extract min. So this will give us the smallest number. And the heap will now take away this number. And then we call extract min again. Then the heap will now report the current minimum, and it is actually the second smallest in the original numbers. So by calling extract min one by one, we will get the n numbers sorted from small to large. Now because insert takes order log n time, and there are n insert operations in part 1, so part 1 takes n log n time. Part 2, we will call extract min n times. Each extract min takes order log n times. So in that case, the second step also takes n log n time. So this one n log n, this one n log n. So it means that the total time is order of n log n. So just asking your friend, we can directly use the heap and then sort the n numbers in n log n time. Now step 1, as mentioned, the purpose of step 1 is to put all the n numbers into the heap. And then we are doing this by inserting them one by one. But in fact, there is an alternative way which is a little bit faster to do so. So we can actually do the same thing. Okay, put all the n numbers into the heap before we can make use of it for step 2 in a different way. And it is faster in the sense that it only takes order of n time. We will show how this can be done. So using this alternative way, we will have a different algorithm because we are using a different step 1. And this algorithm is known to be Heapsort in the literature. However, even if we are doing faster in step 1, the total time is still order of n log n. So mainly what we are going to introduce soon is something just for fun. It will not help in improving the time complexity of the whole method. But in any case, it is interesting. So let's see how we can do step 1 in a different way. Okay, now this new way or this alternative way is based on the following lemma. So let me state the lemma and explain the details in the next slide. So here the lemma says, consider there is a binary tree T, and this T has a root. Okay, the root of this binary tree has 2 children. And then it is connected to the left subtree and the right subtree. But we are given that the left subtree and the right subtree, each of them is a heap. So we are storing numbers inside the nodes, and then the left subtree is a heap, the right subtree is a heap. Left and right are not that related. And then we claim that although this T may not be a heap at all at this moment, but we can make T by doing some changes so that it will satisfy the heap property in order of the height of T time. So what does that mean? So let's take a look of this diagram. So there is a node, and then this node is the root, and then it is storing some value inside. It's connected to 2 subtrees, the left subtree and the right subtree, and it is a heap, and it is a heap. Now we see that this overall thing may not satisfy the heap property. It is because the relationship between the value here and the value here of the roots of L may not be okay. Also, the value of the roots and the value of the roots of R may not satisfy the heap property as well. So there could be problem on this edge, and there could also be problem on this edge. Our purpose is to make the overall thing to satisfy the heap property. So how can this be done? So the idea is exactly the same as we are performing the extract min operation. Because we know that these and these are the only possible edges that could go wrong, what we are going to do here is we compare the roots content and the roots of L and the roots of R and see if there is any violation. If there is violation, then we look at the smaller of these two roots and then swap it with R. So swap R with the smaller of RL and RR. And after that, we do the same process in the remaining parts, and then we will fix the heap property recursively. So the analysis is the same. For each step, this R, the node containing the original root's content, will always move down if there is a swapping. So that means that the total number of swaps is at most the height of this tree. So the time is order of height of t. Okay, so this is a simple lemma, okay, and it is based on the idea that we have already known. But interestingly, we just need this and then to get an alternative algorithm. So for the alternative method to do step 1, what we are going to do here is we are going to put all the n numbers into the nodes of the heap. But then, okay, so we have n numbers, right? So we know how the heap should look like. So we have we first get the binary tree satisfying the shape property, and then we put the n numbers inside. But there is no need to care about the heap property at this moment. After that, we will process the nodes level by level, and then from the bottom level to the top level. And we show that this is done in such a way that after processing a certain node x, the subtree rooted at x will become a heap. And so when we process this level by level, in the end, we are going to process the roots. When we process the roots after processing, the subtree rooted at the root, which means that the whole tree will become a heap. So this is what we hope to do. Okay, so let's see an example run. Suppose that we have a bunch of numbers, and then we want to put them into a binary tree, and then in the end, it is a heap containing all these n numbers. So at the beginning, we just blindly put the numbers inside the nodes without caring about the heap property at all. So we have now all the numbers, but then we see that there are a lot of things that could go wrong. Like 13 and 8, this is wrong, right? This is larger, this is smaller. Wrong, wrong, wrong. But nevertheless, what we are going to do here is we are going to fix the heap property now. We are going to process the nodes level by level. So we first look at this node. This is 24. If we just focus on this node, this is a heap. Just look at this one, this is a heap. So we are done. And now we move to the next node. And for this node, this is just a single node here. If we just look at this part, this is a heap. And now we look at this node. When we look at this node, we see that we are going to look at this part of the tree, and we see that it is not a heap. It is because there's something wrong about the heap property. But we are going to fix it now, because this node connects to a left heap and also a right heap. So we can use the lemma to fix it. So after fixing it, this part is now fixed. So 43 is now swapped with the smaller of these two. So 43 is now swapped with 24. So we get this one. So fixed. So after this, we move on to the next node. Make it into a heap. So nothing is done. And then next node, nothing is done. Next node, nothing is done. And then we look at this one. This is this one. Now this one, we look at the root node. Root node connects to the left heap and the right heap, right? But here, 4 is already okay. It is smaller than both children, right? So in that case, nothing is done. After that, we process this node. When we process this node, we will see that, oh, some violation. So when there is violation, we look at the smaller of these two and then do the swapping. So after swapping, we get something like this 3 is now swapped to 8. And after that, what do? This is the root node. We are now processing the root node now. So the root is not okay. So it is first swapped with this 3 because it is smaller. So 12 now moves to here. And we see that there is also violation. And now 12 is swapped with the smaller of these two. So swap further with this 8. So in the end, 3 moves up, 8 moves up, and 12 is here. So we get 3, 8, and 12. So after processing the last one, which is the root node, then we will get the desired heap containing all the n numbers that we want. Now the correctness of this one is based on the lemma and using induction. So we have already made the claim. So we are proving that after processing each node, the subtree, so after processing each node, so this is the key thing that we want to show. After processing each node x, the subtree rooted at x will become a heap. Okay, so this is the example run. And now we will see that, oh, we are still moving things around. So how come? Yeah, because in some of the cases, like the root node, it may now move up to log n swaps, right? So in such a case, how come we will get a faster method? Okay, so let us analyze the running time. So this time we make a little bit changes here. So we are going to label the levels of the heap bottom up. So bottom level, we call it level 1. Okay. So we see that there are at most n nodes at level 1. Yeah, this is really simple. It is because there are n nodes altogether in the tree. So in the worst case, they are all at the bottom level, but it can't be true. But it is always okay to say there are at most n nodes, right? So there are at most n nodes at the bottom level. Now, because there are at most n nodes at the bottom level, then there will be at most n over 2 nodes at the next bottom level, level 2, because from bottom level to one level up, we are combining 2 nodes into 1, right? And further, there are at most n over 4 nodes at level 3, and so on and so forth. Now, when we process a node at level 1, the time is proportional to the number of nodes up to the bottom. So let's say we spend constant time, 1 unit of time here. When we process the nodes at the level 2, we will go down, right? And then maybe like 2 steps, right? So in such a case, then we say that when we process a node at level 2, that we are going to use 2 units of time. When we process a node at level 3, we are going to use 3 units of time, and so on and so forth. So in that case, the total time will be smaller than or equal to at most, right? Smaller than or equal to n nodes with 1 unit of processing time plus n over 2 nodes with 2 units of processing time plus n over 4 nodes with 3 units of processing time, and so on and so forth. Now let us take the common term n outside. So this is the n. So in that case, the remaining part can be written nicely in this form. 1 plus 2 times 1/2 plus 3 times 1 over 4, which is 1/2 square, plus 4 times 1 over 2 cube, and so on and so forth. It turns out that the sum here is bounded by 4. So if we are summing up to infinite number of terms, then it is actually 4. So altogether, the total time is 4n. Now to see why this is true, let us recall that if x is a small number between -1 and 1, so small number, then 1 plus x squared plus x cubed, so we call this a geometric series. They add up to 1 over 1 minus x. So it is 1 minus x to the power minus 1. Now, but it is not what we want. We want something like 1 plus 2 times a variable plus 3 times a variable square, and so on and so forth. So this is what we want. We want 1 plus 2x plus 3x squared plus 4x cubed. We want to get something like this with x is equal to 1 over 2. So we also want to get the formula for this one. This is not geometric series, but then it is a related sum. So how is the relation of this one with this one? We see that they are nicely related. If we differentiate the left-hand side here with respect to x, then we will get this one. 1 is gone, x becomes 1, x squared becomes 2x, x cubed becomes 3x squared, and so on and so forth. So this part is exactly the differentiated part of the left-hand side. So we differentiate the left-hand side, we get this one. So we differentiate the right-hand side, we should get the right side. And then they are now equal to each other. So by plugging it x to be 1 over 2 in this formula, we will see that this is going to be the number 4. So we see that, oh, this is something that is nice. Now the reason why we are looking like we are doing something similar to the previous case when we are inserting n items one by one. But then how come we are getting something that is faster? Now a closer look of this one is, if we are inserting items one by one, we could have many items at the bottom level or the second bottom level. So many items, like half of the n number of items. And then each of the item here when we are doing insertion, at this case, they need to move up. So they need to spend log n times in the worst case. But on the other hand, in the current method, we have a lot of numbers here at the bottom or the second bottom level. But the time that we spend on them is just 1 or 2 units. So in that case, we only have one node or very few number of nodes spending log n times, but most of the nodes we are spending constant time. So in that sense, we switch the problematic case, and then suddenly we get a better bound. Okay, now let us take a look of the implementation detail. Okay, now so far, if you are very careful about this lecture, you will see that at the beginning we are saying that a heap should have the following shape properties. All levels except the deepest are fully filled, and the deepest level is filled from left to right. But so far in all the arguments, we have made no use of this, the deepest level is filled from left to right. So what does that mean? Even if we do not have this restriction, all the results are still true. We can still perform all the operations in all the log n time. And even we can also perform the heap sort, as we just explained, with step 1 using all the n time as well. So why do we want to get this restriction? The deepest level is filled from left to right. We are making no use of it, and it is not relating or affecting the correctness. But why we want to restrict ourselves so that the heap has to look like this? It is because of implementation. So first, let us now, okay, so it shows the heap, but now I have some brown numbers here written as well. So this brown number is a labeling of the nodes. We are labeling the nodes of the heap level by level, and then for each level, from left to right, we start with root is equal to 1, so that the root has label 1, and then 2, 3, 4, 5, 6, 7, 8, 9. So we do this labeling. Now using this label, we will see that whenever we have an n-node heap, it must be using the nodes with the labels 1, 2, 3 up to n. So if I have a heap that has five nodes, then we are using this node, this node, this node, this node, this node, right? And then they have the labels 1, 2, 3, 4, 5. So what does that mean? It means that if we just want to store the content of a heap, Then we can store it in an array. So node 1 stored at position 1, node 2 stored at position 2, and so on and so forth. So we can store all the items here in an array so that if it has label k, it is stored at the kth entry in the array. And now we also see that, let's say for a node with index x, let's focus on this node 2 here. So the index is 2. Now, what is the parent of this one and what is the children of this one? We will see that we can always find out the parent node will be the one that has index x over 2. So if you divide this number by 2, 2 over 2 is 1, so we get this one. Then we get the parent. Now for this node, this is 3, right? When 3 is divided by 1, then we get 1.5. So we take the floor. So always rounding down. Then we also get the parent. And similarly, to get the children, 2 times the index will give us the index of the left child, and 2x plus 1 will give us the index of the right child. And because of this, although it is a tree, but we actually do not need to store the pointers at all. By storing things in the array, and if we can keep track of which node that we are seeing and the corresponding index, we can easily go up, we can easily go down by finding the corresponding entry in the array that is for the parent or the children. So for instance, let's say we are performing the insertion. So let's say we are inserting the number 5 as a new item here. So what we are going to do, in this array, we are going to put 5 in the entry here because it is the entry for the new node. Now, the shape property is now done, but then the heap property may not work. So we need to check whether there is violation at all. Now the new number is put here and it has index 10. It is the 10th entry here. So we need to find out whether there is violation with its parent. And then where is the parent? This has index 10 for the new node here. So the parent will be having index 5. So we can jump, because this is an array, jump immediately to index 5. 1, 2, 3, 4, 5. This is index 5. And check there is violation or not. If there is no violation, done. If there is violation, we swap. 5, 23, so we swap. And after that, we are now at this index 5 position. So we need to further check whether there is further violation with the new parent. So the new parent is at location index 5, right? So 5 divided by 2 and taking the floor, we get index 2. So the parent of this one is going to be stored at index 2, 1, 2. So this is like this. And then we see that this is 8, and the new value was 5 to be inserted. So 5, 8, we now swap again. 5 is now moved to here, index is 2, so we need to further check whether there is violation with the parent. Index 2, parent is index 1, so we check 5 with index 1 thing. And we see that it is now okay, so we stop. So we see that everything can be done by using this array, as long as we can keep track of the index of the node that we are looking at, the highlighted node. And also, we can access any entry of the array, any random entry of the array in constant time. So in that sense, we get an array representation of the heap. And heap, that's why it's usually introduced when we first learn the data structure course. That's all. Thank you.